very much. Our next speaker is going to be Jonathan Brandmeyer from PlanetIQ. And he's going to talk about PlanetIQ Level 2 data.
Thank you. So I'm Jonathan Brandmeyer from PlanetIQ, and we have built a new Level 2 data processing system. So I'm going to go through a couple of quick performance highlights first, and then go through kind of a life of a profile as we work our way through our system. Before I flip over to the performance highlights slide, I just want to point out the bending angle noise statistic Rob Krasinski presented earlier today was based on an A/B comparison that we had ran between the UCAR SAT-DAC as operated by AER using the receiver's orbit solution versus the production system operated by the UCAR CDAC in support of NOAA, which uses its own orbit determination system. Based on the strength of that finding, where we found that we had better noise statistics with our own onboard orbit solution, we elected to use broadcast orbits for our entire processing system. We found tighter bias and less than half the standard deviation of bending angle noise in the troposphere, in the upper stratosphere when compared against GDAS analysis. Overall, we do see slightly higher bending angle variation in the wave optics region due to finer vertical resolution. We're running our system is at quite a much finer vertical resolution at the bottom of the profiles, and we'll get into some more of the reasons for that later. At the top of the profiles, we are targeting the exact same vertical resolution and filtering parameters that UCAR is using now. Non-Gaussian statistics show a very similar perspective, where median statistics for PlanetIQ data processed by PlanetIQ are considerably tighter against GDAS, as well as the 75th and 95th quartiles. Okay, so talking our way through the order of operations, we're going to work with a Galileo profile, for example, here. Starting with INQ complex data, we record 125 hertz for the pilot subchannel and 250 hertz for the data subchannel. We time match the carrier phase model for both of them. So we're collecting both signals, but they're using exactly the same reference frame. And we've done that so that it makes it easier to combine the pilot and data subchannels on the ground. In this case, each of the subchannels is bringing down 1600 volts per volt square root hertz. And by setting the timestamps to the leading edge of each correlation interval and the carrier phase model at the leading edge of each correlation interval, it's a trivial step for us to demodulate the NAF bits and combine the two subchannels. It's not a difficult research problem to get that done. And in this case, when we've done so, we boost the signals. In all cases, you boost the signal strength by about 41%. In this case, it's over 2300 volts per volt. Now, the receiver's model is good, but it's not perfect. In this case, we've got less than 1 turn of error between the receiver's model and the received signal from a full range of 150 kilometers down to about plus 15 kilometers. But at some point, there will be some disturbance which the receiver's model is not going to track. So here's an example, just crossing probably near the tropopause, where a disturbance in the open loop data shows that the received complex waveform is crossing across the negative real axis. So to solve that problem, we're using closed loop tracking. We implemented a type 2 phase lock loop with the Rockwing-Striegel algorithm. It's an extended common filter in the forward pass followed by a statistical backward pass. That lets us carry information back and forth across extreme fade regions, and means we don't have to play a game of connecting the phase afterwards. We just get to run an ordinary arctan2 across all the data once it's been phase locked. And it is definitely possible to build a PLL which can track these signals, as demonstrated. We implement it by calculating a fix-up to the receiver's reference frame and add that to both sides of the reference frame. So we're still maintaining the data as an unevaluated sum of a reference frame and a complex residual with respect to that reference frame. Okay, geometric optics, fundamental equations. I'm not going to spend too much time on this since we're way over time. It's exactly the same as ROPP's representation with slightly different choices about inertial coordinate system and timestamps. We've chosen an Earth-centered inertial frame at a canonical epoch for the whole occultation, process everything into a local inertial frame, perform all the processing that way. And that way we don't have to deal with the pull files or rotation to any kind of celestial reference frame or a global canonical reference. We can just use a local inertially correct reference frame. Now for the ionosphere correction, we've made a slightly different choice. So previous research has focused on building an ionosphere correction of a single frequency profile plus a filtered, scaled version of the difference between the other two signals. And the reason you might do that is if your L2 signal is particularly noisy, as is the case for semi-codeless tracking. Our receiver has been built with high performance reception for both the L1 and L2 signals. And so for our case, we found that in all profile cases, the best choice is to perform the direct linear combination for L1 and L2 without any additional filtering on those two to come up with the ionosphere correction. When looking at this graphic, showing? No, this button. There we go. So recall that the limiting resolution for geometric optics is typically the first Fresnel zone at about 1.3 kilometers. So that's out here. So here we're showing a case where we've just performed basic phase combination to form the L3 linear combination. We're showing that in the modified element deviation. So we can see that in this region where we're dominated by white noise, eventually the ionosphere noise, the ionosphere's effect starts to dominate the signal. The basic L3 combination is still lower noise than either L1 or L2 alone. So we know even after performing the linear combination that we aren't making the signal any worse by doing that. The result is we get extremely clear profiles, even well above 60 kilometers. So it's so good that we have to wipe off an exponential trend when we're calculating the standard deviation of bending angle noise between 60 and 80 kilometers. In this case, that after wiping off that trend, we're down to 0.2 microradians of bending angle noise, right? Now for us, the entire geometric optics exercise really existed to provide an extrapolation that we could use for wave optics processing. Our extrapolation method is very similar to the process developed by Ms. Zhang at UCAR. So nothing really surprising there. Now for wave optics, we've implemented a method that is similar to Sievert's sliding window phase matching with a couple of key differences. The first difference is that we are using the full phase matching chirp signal when down converting the received signal down to lines of constant impact height, instead of using a kind of bending angle local approximation. So Sievert described a method where you calculate kind of a local derivative to the phase matching model and use just that local derivative for down conversion. In our case, we're using the full phase matching model. The next is that we're maintaining the signal model as a phase continuous reference, as kind of an unevaluated sum of phase continuous reference frame and the complex wave field with respect to that reference frame. We use the phase matching kind of chirp-like model to transform that wave field instead of using a geometric optics global excess phase estimate. So that gives us more freedom to choose what our reference frame is going to be. Lastly, we low-pass filter the transform complex field to identify a bending angle at each impact height. So why do we do it at all? It's the same reason anybody runs a wave optics method, is so that we can transform atmospheric multipath munged pile of mud into a clear picture, mapping the signals to the bending angle and the impact height domain. What capabilities do we get from this method? First off, it's insensitive to the receiver's choice of reference frame. Previous researchers have previously reported that there is an inability to recover sharp bending angles due to open loop model tracking errors. Right, sliding window phase matching can recover sharp bending angle versus impact height transients without any dependency on the phase model. So when we look at these sharp steps here and here, and here. Every single one of those represents a steep gradient in the vertical and a steep vertical gradient in the index of refractivity. We want to recover those vertical gradients to improve analysis in the lower troposphere. This graphic shows contour lines, where these contour lines are a frequency offset between the phase matching model and the reference frame of what's being fed into the wave optics processing. So in this case, I'm showing the receiver's model, and the red line is the DC point for the receiver's model in this profile. Here's the exact same analysis using the Rockström-Striebel PLL model that we calculated for the geometric optics result earlier. The exact same result. Here's the exact same result again, taking the receiver's model, smoothing it, and perturbing it with a 15 hertz error. 15 hertz was way beyond what previous folks have described as kind of a limit for being able to recover those peak bending angles. Now we can do it. Next up, it's insensitive to cycle slips because we never make a noise-dependent connected phase decision. It never has cycle slips. Never has cycle slips because we're not really even counting cycles. So when the signal supports it, now it's usable for ducting height estimation. So this is a case where this is a signal which has likely been identified as ducting. The profile is going all the way out to about negative 350 kilometers below the limb out here. And all this signal energy is related to one of these sharp bending angle peaks. Now, sometimes it's not super clear to identify which bending angle peak that comes from. But in other cases, it's extremely clear. And so we're using this as an aid to identify exactly when ducting is occurring and at which height it's occurring. Next up, it's insensitive to track depth truncation. So researchers have reported that positive bending angle biases due to noise entering wave optics from deeper regions in straight line tangent altitude. So all this area of noise out here, when ingested in wave optics, kind of pollutes the best estimate for minimum phase in this profile. But because we're using a locally filtered version of the signal, the amount of signal which contributes to every individual bending angle versus impact height coordinate is entirely consistent. It doesn't matter where we truncated the signal. We get the exact same result if we truncate it here or we truncate it all the way out here. So we can process these extremely deep profiles without worrying about introducing bending angle biases. Next up, for reflection processing, reflection signals are routinely collected as a side effect of radio occultation signal processing. There's been a lot of proposals on how to extract additional information about the lower troposphere from those signals. Here's an example of a GLONASS track where we can see the reflection signal crosses the Nyquist band, wraps around, crosses DC again, crosses the Nyquist band again, and keeps on going. That's partially a side effect of GLONASS's extremely wide chip modulation. That's a 600-meter chip modulation. So we pick up those signals really deeply. Now, normally when we're processing wave optics, we set up a guard to avoid performing those integrals across the Nyquist bands. But if we can clear that guard, then we can collect that reflection signal, pass the Nyquist bands, and assemble it into a more complete bending angle versus impact height interpretation of that reflection signal. Next up, we've added some aids to support 4D variational assimilation, starting with time. So every single one of those little low-pass filter coordinates has a time coordinate associated with it as well. And so we're putting those time coordinates in our files, not because we think that 5 seconds or 10 seconds really matters for 4D VAR, but because it serves as an index back into the geometry information. So when somebody is running a 2D bending angle forward operator, we think that it would be helpful for the data to meet the forward operator. 1 minute, thank you, ma'am. For the forward operator, for the processing system to meet the forward operator halfway. To illustrate how much the tangent point's moving, we can loop back through the geometric optics equations and see where the bent path tangent point is being perturbed, right? These lines are 25 kilometers per major tick on these contour lines, which I picked because it's close to a simulation window grid cell size. Fast forwarding. Okay, last up, polarimetric RO processing. So polarimetric RO data is, we just launched, we got scientific operations less than a day after launch. Woohoo! We're tracking all 4 worldwide GNSS constellations on it. We're tracking dual frequency for every single one of them. That's a total of 6 bands. Now, with sliding window phase matching, the H-V phase shift determined is easy. We just take the conjugate of the complex conjugate product and we get the phase shift. And because we never need to fix up cycle slips, and therefore we can get polarimetric RO in bending angle and impact height space. Now, we're really, really excited about this, but this analysis is about a week old. The one thing I don't have to show, unfortunately, is concurrences against radar. But this is the kind of signals that we were expecting to find for heavy precip, maybe more heavy precip, probably not any heavy precipitation, and maybe freezing line indications. Okay, so summing up, there is high performance available in the upper stratosphere without ground-based POD, high rate clocks, IGS orbits, without any climatological model whatsoever in the processing system. This is 100% observations all the way to the top. And this is some of the fundamental work that PlanetIQ is doing to advance the state of the art in radio occultation and advance its capabilities in the lower troposphere. Thanks for your time.
Okay, thank you very much. Since we are already out of time, I suggest we move the questions to the lunch break.